Good. Sorry for the delay. Let's pretend for a second that I am Claudio Bonati, who is a bit unwell and asked me if I can give this talk. This work is done in collaboration with all these people, and these are based on this work. And we will discuss about the theta dependence in the deconfined QCD. This is the outline of the talk. First, I will introduce the theta dependence of QCD and discuss why is it important. I will tell you a bit about the analytic approach that one can use to study. Should have not done this, but and then I will give you our lattice results and draw some conclusions. The theta term can be inserted in the QCD Lagrangian in this way. So inserting, adding a term I theta qx, where q is effective basically. The integral of q is the topological charge, and this quantity, which is a total divergence, and this is the behavior that the U1 axial transformation, which we will use in the following. So under the U1 transformation of this kind, theta goes to is shifted, and the mass term gets a phase. One can decompose the free energy in presence of the theta term, and in power of the theta term, and this is the expected form of the free energy. The dominant term is the topological susceptibility, which is basically the expectation value of the, well, it's basically the variance over the volume in the limit of the infinite volume. And then you can define higher moments which parameterize deviations from the purely Gaussian behavior that you would have in their absence. There are several properties that one can discuss. For example, the free energy is even in theta, because the partition function is, and there is a bound that that one can draw by using Schwarz inequality. One can easily show that the free energy in presence of a theta term is larger than the one in absence of a theta term. The theta term is related to, and topological charge is related to a rich phenomenology. For example, here we have the famous Witten-Veneziano formula that relates the mass of the eta to the topological susceptibility. And most notably, it's related to the strong CD problem. Experimentally, we have that this theta term is very, very small from the EDM electrical moment neutral measurement. We have a limit of disorder, which is a very small number, and we don't know why this is happening. There have been several solutions proposed to this problem. The easiest one is that if you go back to the U1 transformation I showed you, you can easily see that if at least one of the quarks is massless, there is no dependence on theta and the Lagrangian. Another possibility is that the full Lagrangian of standard model is actually symmetric, and the TP variation is induced by some breaking of global symmetry, and then spontaneous breaking. And most appealing is the possibility that this angle is dynamical in this sense. If we replace what was theta with if we add the Lagrangian term in which theta is replaced by this A, which is a pseudoscalar field with only derivative interactions, one can see that as this A gets dynamical properties, the free energy relation that we discussed just one slide ago implies that the vacuum acquires an expectation value in such a way that the effective total theta term is minimized, and this would imply eventually a very small, if not null, effective theta angle. This can be achieved by means of getting this A field through a breaking of the U1 axial from the U1 axial symmetry through from spontaneous breaking, in which this axion with field A is the Goldstone boson of the broken symmetry, and the effective QCD Lagrangian for this pseudo-Goldstone boson, which is called Axion, has this form. This particle has been searched, the Axion, for a long time. There are several bounds on its existence. This is a recent picture, and one can see that there are bounds on different origin, so from cosmology, from direct observation, and there are small windows that are left free from bounds. This picture will change depending on the model, but this is the qualitative behavior that you expect. It will depend on the details of the model. So there are, because of the mass, because of the fact that the mass is related to the coupling, one can see that the bounds currently suggest a very large coupling. So one can use simplifications and draw some relation to the axion mass, which at tree level has this relation between the topological susceptibility, the coupling, and the mass. Why is this particle appealing? Besides treating the CD problem, is also a candidate for dark matter. So you get two solutions for one single particle, which is great. Then axions can be produced in a various mechanisms, and the most interesting is this misaligned mechanism, for which, if you study the cosmological evolution of the field of the axion, which is subject to this equation of motion, there are three stages of this evolution. At origin of the universe, this field A will be constant because the Hubble constant is very large, and this term dominates. Then, when the mass becomes approximately the same order of magnitude of H, the field starts oscillating, and then you have a freezing, and in which you can use an approximation and compute the final number of axions that you get, which turns out to be conserved in the comoving frame. And I think Daniel has a picture in his slides. I couldn't resist from having a glance at them, so you will see an actual plot of this. From this you get another closer bound, because the axion density must be smaller than the dark matter density observed. So this is one of the bounds on the axion, on the properties of the axion, that is what we aim at studying in details. There are several tools that one can try to use to study the properties of axions. For semiclassical approximation, one can write a theory in which describe the system in terms of weakly interacting classical configuration, which are instances, and one arrives to with direct instanton gas approximation, from which the partition function can be computed, and the free energy has this form in which the topological susceptibility is the constant in front of everything. One can go beyond and use observe that fermionic degrees of freedom suppress the topology because of zero modes, and one can compute the first moments of the distribution. So the full expression we have this form, in which enters this S0, which is the action of a single topological object, a single instanton, which has been computed a long time ago, and has this form. So there are various tools that one can think to use to study the free energy, and then get information on the evolution of the axion field at cosmological time. There is another tool, of course, which is Chiral Perturbation Theory, from which the properties of the axion can be computed. In fact, the theta term, which is not so nice to be treated, can be eliminated in favor of a complex matrix through an U1 rotation. And then Chiral perturbation theory can be used as usually. So recently there have been precise calculation from one of the authors of the paper that I'm discussing and his collaborators, in which the topological susceptibility and the moments have been computed to high precision, and you get these numbers for the topological susceptibility. The fourth root is about 77 MeV. Can we trust this approximation and where? So instanton calculation based on instanton are not easy at zero temperature, because they need a prescription in order to treat the divergence, which is not present at finite temperature because the temperature acts itself as a regulator. On the other hand, Chiral perturbation theory goes by itself that cannot be used at temperatures larger than the confinement, simply because there is no chiral symmetry breaking. So we have to do something in between the t equals 0 and the very large temperature. One can only use lattice to, well, it's tempted to use lattice. On the lattice there are several problems to be solved. The topological charge is defined only as smooth configurations, and the configuration that you have are not smooth. So one has to treat these. Several proposals have been used. The field theoretical, based on fermionic definition of the topological charge, or based on smoothing. There are various ways, but the bottom line is that all the reasonable methods have been proved to be equivalent, close to the continuum limit. And for what it matters now, we are using cooling. The other more serious problem is that the topological charge gets slower and slower. The evolution of the topological charge gets slower and slower in our algorithm when going to the continuum limit, simply because the configuration space is getting partitioned in different topological sectors, and our algorithm works by making a smooth transformation. So it gets more and more complicated to go from topological sector and another one when this topological charge gets more and more well defined. So you see an example from our work of the fact that on the same time evolution scale, the topological charge evolve quickly, evolve less quickly, and then get stuck, or as we like to say, get frozen. So there have been several studies in the past in the pure Yang theory, which are I try to collect here, and from various groups, and these are just some of them. Now I want to show you our results, which are based on an f equal 2 plus 1 simulation on the physical quark mass. This is the study, our benchmark, in which we have computed at zero temperature the topological susceptibility and compared with the Chiral perturbation theory estimate. You can see that our data, which is these 5 red points as a function of spacing, has quite significant cutoff effect, huge cutoff effect. But if we concentrate on the 3 smallest lattice spacing, we are able to make a sensible continuum limit extrapolation and get results in agreement with Chiral perturbation theory. You can see that the result is significantly, there is a substantial extrapolation, but the result seems in reasonable agreement with expectations. So this gives us confidence that we can do something at finite temperature, which is what we did. And here I show you the fourth root of the topological susceptibility as a function of the temperature in units of the confinement temperature in log-log scale, because the dielectric gas approximation predicts a power law behavior of this topological susceptibility, and then it's convenient to draw this in log-log scale. You can see that the 3 smallest lattice spacing that we have employed are this one, and there is a substantial difference between the results obtained with the 3 lattice spacing, but each of them individually lines quite nicely on a line, which means that we are following some power law. So it is tempting to fit them with these ansatz in which we are assuming a power law and a prefactor which depends on the lattice spacing, which effectively parameterize a global shift over three lines. So this is the continuum limit extrapolated result obtained with this global fit, and you see that there is quite a significant difference between the free lattice spacing and the continuum. In this region, you can see we have only two lattice spacing and eventually only one here. But here we have free lattice spacing, and we are quite confident that on the basis of what we have observed at zero temperature, this should capture the continuum limit behavior. We tried another strategy, which is to study the ratio of non-zero temperature over zero temperature susceptibility, which show a significant reduction, impressive reduction of the cutoff effects. You can see that now, when I divide by the result at zero temperature, the susceptibility of the free lattice spacing gets really sitting one on top of each other, and the extrapolation to a constant without any with a similar fit give a very similar results with what I showed you before. So the combination of these two gives us confidence that we are extracting continuum limit physics. And here I compare the result with two models. KPT, which you wouldn't trust beyond critical temperature, and direct instant on gas approximation, which predicts a power law with an exponent of about 7, 8. Whereas we find a much milder, much smaller exponent of the order of 3. This is quite interesting, and would be very interesting to study if this holds really also in this region, in which we are not we don't pretend we are doing a series extrapolation because we have only two lattice spacing, but in this region we are really seeing something which is much milder than the direct instant on gas approximation. Whereas we have studied also the first cumulant B2, for which direct instant on gas approximation suggests a very quick decrease to minus 1/12, and we see some deviation in between 1 and 2 TC, which would be interesting, but only at the finite lattice spacing. So this would be much interesting to study more in details, and would suggest that there are interaction between instanton mediated by quarks, because this deviation is in opposite sign of what observed in the pure gauge theory. All of this leads to a quite significant modification if you trust the exponent we have determined from our study of the topological susceptibility as a function of the temperature, and would change the window for which the axion is a valid candidate for dark matter by almost an order of magnitude. So it would be very interesting outcome of the work if taken at face value. There has been huge activity over these last few years, and I will not cover all of them. There are really many, but more recent works by Tversky and Al is based on similar study of ours, but with a couple of finite lattice spacing, finite points, if you want, and these additional points gets to them a huge change in the results of what the susceptibility looks like. They have still large cutoff effects, but with these points they get a much more closer results with the direct instant on gas approximation. Even more recently, the group of Folder and company, which several which one of the authors here has repeated the study based on a very different approach, which I like it a lot, and is based on the integration thermodynamical integration to determine the susceptibility. They address two different problems. In one way, they solve somehow the topological freezing by not studying by brute force the topological evolution, but concentrating on two sectors of a fixed topological charge. And we try to address the continuum limit by making a reweighting to make chiral symmetry more exact. So this is a new approach that I've never seen before, and I'm eager to learn more. But all these change, all these modifications of the procedure, this also in their case to a much more in agreement with the Deviations gas approximation results. And I would like to understand a bit better how this zero modes reweighting affects the results and how independent of the assumption is. But this is a certainly interesting result. And of course, there are other studies by Axion, and there is a poster site, so have a look if you're interested. Our conclusion is that in our work we observe a slower convergence to the instant-on gas approximation, which might be related to attractive interaction between instantons. Chiral susceptibility gets strong deviation from the instant-on gas approximation, and this would lead, if taken at face value, to a one-order modification of the window of validity for the axion mass. In the future, we plan to check for discretization effects going to continuum limit in a closer way by trying to use new algorithms and to this way maybe go to a higher temperature with more lattice spacing. Thank you for your attention.
So we thank both Claudio and Francesco.
How important is chiral symmetry in your work?
So, chiral symmetry is vital because you can see that with huge extrapolation from 150 to 70 MeV is due to the fact that in a staggered at least the full taste multiplet is not degenerate, which is related to the fact that the full chiral symmetry is not completely whole. So this is in fact why BW group has used this approach of zero modes reweighting, which I like, but it's really new, so I need to understand well what is it about and how independent of assumption it is. But this is certainly one idea to address this problem.
I have the same question about the same site. So the paper by Bonati then finds also this t to the minus 8. And
yeah, but
that's maybe closer to the method that you use.
That method is very close, and to my opinion, and there is nobody from this paper here, so I don't want to be. But they are adding just a few points with a smaller volume than the others, and they find a smaller fluctuation of topological charge. So in this picture, it is like if I added some extra point here on a final volume and on a final lattice spacing, but also on a smaller volume, which in fact I think it's driving a lot the extrapolation to the continuum in their case. I mean, we've tried and it seems that this is really the leading thing. So, I mean, it's not the global picture that changed, but there are a couple of points that, but they are in the corner in which you don't really trust your simulation too much. So I don't know how much this adds to the.
How do the decorrelation issues that you mentioned, how do they vary with temperature as you go
with
through
temperature? So temperature has the effect of shrinking the distribution of the topological charge because the topological susceptibility is basically the variance over the volume, full volume, and it makes such that you see even less fluctuation, but also because the variance is reduced, so you get less changes. But I don't think I don't think it affects the actual slowing down of the topological charge. It is going to shrink for sure the variance, to reduce the variance, and so you will observe less fluctuation, but for a physical reason, if you want. I don't know if you have comments on this.
But I will talk a lot about this topic.
No, I mean about the topological charge, the correlation. I think it doesn't change the slowing down, it changes the variance and the...
Can comment on one first thing, just as an author of this other paper by Bonati, it has of course a reason why we started with all these new methods with overlap fermions and this elaborate analysis, and it was that initially we wanted to use the original method as you did, and our action is very similar that you are using in us. And then we also had this n to 8, n to 10, n to 12, it was perfect continuum limit. And then we had n to 16, n to 20, n to 24, n to 32. It's still tunneled. Yes, we did these simulations, and the continuum extrapolation was jonks. And then we said, oh, it's impossible with standard fermions. So that's why this long paper.
Yeah, I think there are several issues to address. It's just I don't know if it's a new technique that I want to understand better. It's not. And probably if you apply something similar, it's possible that your result is the reliable one, but I think we have to check independently with possibly a different approach, because it's all new and we don't know what to say about it.
So, thank you, Francesco, and we thank all the speakers. I think we are supposed to be back at 11:05.
Posso riprendere la mia morta chiavetta?
Sì, sul tavolo lì.
Sorry. Sorry. Devo mettere in